So assignment materials, we did first 10 questions. Today we'll do 10 onward. Question 11. The graph shows the behavior of a brittle and a ductile material. Use the graph to help use the graph to help you describe brittle and ductile material. So using the graph, how you can define a brittle or distinguish between brittle and ductile material? You can see for a brittle material, there is no or little plastic deformation before the object break. So using the graph, you can identify easily. So you just have to write a definition here that from this graph, you can say that there is no or little plastic deformation before the object breakdown. But ductile, and one more thing, like ductile, what is the difference between malleable and ductile? Malleable means it can deform under compression, and ductile means it can deform under stretching force. Like if there's an object, say a metal is there, and we are applying a force and deform, then we say it is malleable, like it is deforming under compression. But if we have a metal and we apply a force to stretch the metal, in that case, we say this object to be ductile because it deform under stretching. So deform under compression, malleable.
Sir, what happens to the area in malleable and ductile objects?
The total surface area will change.
Means it will increase or decrease?
Here we are compressing. So when you are compressing something, it means the surface area will decrease. Here we are stretching an object, so surface area will increase. But the total volume remains the same. Like if area is changing, the length will also change, like one of the dimension, but the volume will remain same. Here, if what happens, if area is decreasing, in terms of length, it should increase so that volume is constant. Here, what happened, if we are stretching it, if area is increasing, it means the length should decrease, other way around. Or if area is decreasing, then the length should increase. Here, if area is increasing, then when we compress, the length should decrease. So for a brittle material, it will deform under compression. And for ductile material, object can undergo, like this graph shows that it can undergo greater or a larger plastic deformation or more area under the graph. Shows that there's a large plastic deformation under tensile stress. Tensile stress means like when we apply a force to increase the size, we call that as a tensile stress. And when we are applying a force to reduce the size, we call that as a compressive stress. So if object undergo a plastic deformation under a compressive stress, we call that object to be malleable. If object undergo a greater deformation under tensile stress, we call that as ductile. So large area in the graph shows for a ductile material, large area under the graph will show that greater plastic deformation. And because it's a ductile material, so you have to mention undergo, like, or you can say under tensile stress. Is it clear, this one?
Yes, clear.
Next is, in 2016, the 3 Chinese vessels dating from 17th century were smashed when a man fell down the stairs, and a restoration expert put the vase back together, and she said it wasn't difficult. It wasn't a difficult job. The museum collect all pieces and they fit it back together perfectly. Explain why it was possible to fit the pieces together perfectly. Like for a vase, when it break down and it was made up of porcelain, so why it was easy to just fix or arrange or fix the pieces? Because what happened, the vase is normally made up of a brittle material. Brittle material means like it does not go under a lot of deformation or very low, very little plastic deformation. So the vase is made up of a brittle material, so it undergo a little, no or a little plastic deformation, so it does not change the shape much. Like this, when it break down into pieces, the pieces does not change. Like example, it break down, but it does not change the size of the piece. As a result, what simply if we want to fix, we just have to combine that or fix the piece in a correct order so that it will form the same figure again. That's why, like if a brittle object break down, as the particles in the small pieces does not undergo any deformation or a large deformation, so we can fix them together. So why it is possible to fit the pieces of back together? So the answer here that the vase or made of brittle material, and as a result, what will happen? The pieces does not undergo or no or little plastic deformation. So we can fix the pieces or combine the pieces together like a jigsaw puzzle that we can combine or fix the pieces together. Same thing happen as it does not undergo a deformation. Now, otherwise, if it undergo a deformation, then it will be a difficult thing to perfectly put them together. In question 12, a slinky is a long spring made of metal. One end of a slinky is fixed to a ceiling, the roof. The force acting on the slinky was varied by hanging a weight from the other end. The graph shows the result. So the graph is representing the result. Explain whether the results follow the Hooke's law. So we have to, this is a graph is there between the length, but the idea is that because if something obey a Hooke's law, it should be a straight line passing through origin. It is a straight line, but it is not passing through origin. So it does not, like force and length are not directly proportional. So if you mention like Hooke's law is not stating that force and length directly proportional. Hooke's law states that force and extension are directly proportional. So what you have to check, like if this was a graph for force and extension, then it should be a straight line or passing through origin. So as the length is increasing, it means the extension will also increase. Like here, when the length is about, each box is representing 5, each box is representing 10. So this is 160, the length is 160. So when the length is 160, extension is 0. But when we apply a force of 0.1, it will become about 170. Then it become about 180, 200. So it means extension is increasing with us as we are increasing a force, extension is also increasing. So a straight line with a constant gradient, so the extension or the change in length is like the extension is also increasing with the same rate, or we can say force and extension are increasing. So it means it will obey a Hooke's law. Because so the answer is yes here, not no. Why? Because we are Hooke's law state force and extension are directly proportional. This is a graph for force and length. So using the length, you will determine the extension, and using the extension, you can work out whether it is obeying a Hooke's law or no. So we will say yes. So it is a straight line which shows change in the length increase with the force. So when the length is increasing, when the force is increasing, the change in length is also increasing. But what if it was a curve? Like the same was there, the graph between length and force, and it was a curve. In that case, like say this was a curve. In that case, we will not say that it is omega Hooke's law. Why? Because when we are increasing the force, the change in length is not same for every increase in the force. Show that the stiffness of a slinky is about 0.7 Newton per meter. So stiffness, how much force is needed to produce 1 centimeter, 1 millimeter extension? So how to work out the stiffness? You can take like here when the force is 0, we can also find the gradient because the gradient will give us a value of the K. Or you can also use the 2 points. When the force is 0 newtons, it was 160. When the force is 0.4 or say 0.5, it is 230. So force is 0.5, this will be 230, but that is in centimeter. So 230 minus 160, and we need the final answer in Newton per meter, so we have to convert. So 230 minus 160, which is 70, and that 70 will be centimeter, but that is in meters, so 0.7. So we have the extension, the change is there, that is 0.7, and the force which change is 0.5. So stiffness is force divided K, stiffness, so 0.5 divided by 0.7. So 0.5 divided by 0.7 will give us 0.71 Newton per meter. So that was the question itself, that we have to show that the stiffness of the spring is about 0.7 Newton. Calculate the elastic strain energy stored in the slinky when the force is applied. Force applied is 0.7. Elastic strain energy is basically the area. You can use the area under the graph or half force into extension. Either you can use area under the graph, or the elastic strain energy is given by half force into extension. So half force is 0.7. And what about extension? For extension, we have to check the graph. So when you check the graph for a force of 0.7, the length is 260. And this was 160. So 260 minus 160, that's equals to 100. 100 centimeter, or will divide by 100, so it will be equal to 1 meter. So it will be half force into extension. So it will be force into extension. So force is 0.7 and extension is, it's 100 centimeter, but because SI unit of the energy is joule, so we should have force in Newton and distance in meter. So Newton meter is actually given you. So it will be 0.35. The work done is 0.35. Joules will be there, the elastic strain. Explain the difference between, question 13, explain the difference between compressive strain and tensile strain. So what is the difference between compressive strain and tensile strain? Compressive strain means, like if an object can undergo a deformation, a large plastic deformation under compression, We call that as a compressive strain. And if an object can undergo a large plastic deformation under tensile stress or tensile force or under tension, we call that as a tensile strain. Strain, because the definition of a strain, it is simply the definition of a strain, it is a comparison of change in length compared to original length. So how much the length changes compared to original length, that is called strain. And what is compressive strain? So compressive strain means if an object can undergo plastic deformation under compression, we call that as a compressive strain. But if an object undergo a plastic deformation, a large plastic deformation under tension or tensile force or tensile stress, we call that as a tensile strain. So like force is applied to reduce the size. So how much the size changes compared to original, we call that as a compressive strain. But force applied to increase the size, so how much force is applied on so that the object size or how much size increase for an object compared to the original size, that is known as tensile strain. Is it clear discussion, Tony?
Yes, clear.
A student investigates how the length of a spring vary with the force by hanging masses on it. The graph shows the relation. So again, if the student concludes that the spring does not obey Hooke's law because the line does not pass through origin. Explain why this conclusion is incorrect. Yeah, why this conclusion is incorrect? Because Hooke's law is not a statement between force and length, it is a statement between force and change in length. So what is happening? The graph is for length, not for extension. According to Hooke's law, force and extension are directly proportional. And not the force and length. So according to like student write the statement according to force and length, and he concluded or she concluded that it is not obeying a Hooke's law, that force and length graph is not starting from origin. But that's not true, because the Hooke's law is showing a relation between force and extension, and it is a straight line which shows the extension is increasing with the same rate as we are increasing the force. So why this conclusion is incorrect? Because student consider length, not the extension. And the second thing, what happened? That student, like Hooke's law shows a relation between force and extension, which are directly proportional to each other. So in this case, the force and extension are directly proportional to each other. As it is a straight line, so it means the extension is increasing with the same rate as the force. Show that the spring constant or the value of the K is about 30 Newton per meter. So again, we have to use a graph when the force is 0, when no force is applied, it is about 2.5. That's the first point. So 2.5 when the force is 0. And example, say this is when it is 5 is 20. But as you can see, most of the question, they give you the values in centimeters, so don't forget to convert into meters. So this is 2.5, this is 20, so 20 minus 2.5, which is 17.5 centimeter. We divide by 100.175 meters will be there. And the force is 5. So that's the force 5 is there. So to get the spring constant or K is equals to force divided by extension. You can represent extension by delta x or you can represent by E. Normally they represent by delta x. So this F is 5 and extension is 0.17. So F divided by means 5 divided by 0.17. That's equal to 28.5. The spring constant for this spring is 28.5. The next part, when student is removing the mass, the spring is accidentally released when its length is 23 centimeters. The spring flies up into air. Show that the energy stored in the spring is about 0.6 joule when the length is 23. So how to calculate the energy stored in the spring? The energy stored in the spring is half force into elastic strain energy, half force into extension. So because what happened, like the length of when student is removing the masses, this spring is accidentally released when it is 23 centimeter and it flies up into air. So we have to show that the energy which was stored in the spring is about 0.6 joules. So what we will do, first we'll find when the length is 23, because half force into extension. How to get extension? Original length is 2.5, new length is 23. So it will be 23 minus 2.5. So 23 minus 2.5, that is 20.5. So 20.5 centimeter, we convert into meter. So 0.205 meters, that is extension. But how to know the force? So to get the force, you have to use the graph. When the length is 23, how much is the force? That you have to use a graph. So length 23, each is representing 1, so 21, 2, and 3. So that is 5.8. So using the graph, we work out that the force is equal to 5.8. So we'll substitute 5.8 here. So 5.8 multiplied with this will give us how much energy is stored. That is about 0.59 joules. The next part, calculate the maximum height the spring could reach above its point of release. Mass of the spring is 5. So basically what happened? When the spring suddenly released, the elastic strain energy changes to potential energy. And we assume all the elastic strain energy changes to potential. So potential energy is equal to elastic strain energy. Potential energy is mgh. Elastic strain energy that we calculated was 0.59. This was 0.59 joules. So we have to convert the mass is there, which is given in gram. We have to convert into kilogram. So it will be 0.005. Gravity is 9.81 multiplied by height is equals to the elastic strain energy 0.59. And if we need height, we divide all of them. That will give us a height which is about 12 meters. So it will rise to a height of 12 meters and the elastic strain energy. And what is our assumption? We assume that all of the elastic strain energy converted into gravitational potential energy. Like there is no loss of energy. Several other students carry out similar investigations using identical springs. The photograph shows some of the springs at the end of their investigation. Spring A is same length before and after the investigation. Means spring A does not undergo a plastic deformation. The graph shows the graph for spring A is there. On this axis opposite, on the axis opposite, sketch a graph for spring C and use to help describe a difference in behavior for A and C. So when you check the photograph, you can clearly see that A returned back to the same original place. So A does not undergo deformation, plastic deformation. But C, like it does not return back to the same original length, so it undergo a deformation or a plastic deformation. So how we complete the graph? So first example, C is obeying a Hooke's law because it's a straight line. Then when we are increasing a force, extension is length is increasing with a greater, then like this point X is representing elastic limit. Elastic limit means after this object will not return back to the same original length. And then when we return, like we remove the force, it will deform. So it will have a new length will be more than the original length. Like maybe we started with 2 centimeter spring, but when we complete the experiment and the spring deformed completely, maybe it is 11 centimeter. I'm just giving you values. You can write in your own way. So this is there for, and for A, because A does not undergo a deformation like a plastic deformation. So if we draw, it will return back to the same original length. So mark is there for drawing. Then description, like what is the reason why C undergo a deformation but A does not? So the reason is that it means more mass is added for a spring C, and spring A is not extended beyond the elastic limit, beyond the past the elastic limit. C is extended beyond the elastic limit. Spring A will show a elastic behavior, and spring C will show a plastic behavior. And C deform permanently, where A does not deform permanently. So the mark distribution, if you may like draw a continuous line, like drawing these lines, marking a limit of proportionality, that will give you 2 marks. And then the explanation is there for why C undergo a plastic deformation and A does not. It means for C, we use a greater mass as compared to that of A. Is it clear?
Yes, clear.
Okay.
Yes.
Then a cylinder of length 50 centimeter has a force applied to it. The new length of a cylinder is 45. The quantity determined using 5 centimeter to 50 centimeter is like we are comparing a ratio of change in length over original length. So what it will be? So it cannot be stress, because stress is force acting on unit area. So any option with a stress is wrong. We have a compressive or tensile. So which strain is this? Like, because strain is a comparison of change in length over original length. Which strain is this? Compressive strain or tensile strain?
A compressive strain.
So compressive strain, because we reduce the size, that's why we say it is a compressive strain. So A will be the right answer. Then 3 spring X, Y, and Z, and this is a graph for length. But because even a length and force is a straight line, it means here force and compression are directly proportional. Here force and extension are direct. But it is a curve, it means force and extension are not directly proportional. So which two are obeying the Hooke's law, X and Y? Because force is directly proportional to compression, or extension is a relation for the Hooke's law. So force proportional to extension or compression. So these two graphs are correct, but this one is not. So A will be the answer. Then in question 17, student read the following statement in a textbook. Unlike many metals, lead is malleable, not ductile. So why it's a 4 marks? So you just have to write the definition, like what is the mark distribution. First thing you will mention, malleable material means it will undergo a deformation or permanent plastic deformation or a larger plastic deformation before breakdown under compression. That's malleable. And ductile means it will undergo a large plastic deformation under tension or a tensile force. So one mark is for mentioning undergo a large plastic deformation. One mark is for mentioning compression. The second mark for like the ductile, large plastic deformation or permanent deformation. And again, that will be under tension or tensile force. Next is question 18. The graph shows a stress and strain curve for two types of human bone under compression. One is the cortical bone and another one is trabecular bone. Use a graph, identify and describe one property of the cortical bone. So what is the property of the cortical bone? The cortical bone does not undergo a large deformation or very small plastic deformation. So it means it is a brittle. Or you can also mention, because it is much steeper, as you can see, the slope, this is a higher slope. So it is much steeper than this one. So we can say so you can also mention it will have a higher Young's modulus, or it is stiffer. Then the table gives the following information about the two types of the bones. State the difference between compressive stress and tensile stress. So compressive stress means force acting on unit area to reduce the size, where compressive stress would shorten the bone, like reduce the size, and tensile will stretch the bone or increase the size. Then how the graph show could be used to confirm the value of the Young's modulus of a cortical bone. Like how we can find the Young's modulus of a cortical bone. So what we can do, we can just simply find the gradient of a straight line, not the curved part, the gradient of a straight line to get the value for Young's modulus. A person of mass 90 kilograms stand on 1 foot. Show that the maximum weight which can be supported about is 70 times the weight of the person. Assume that all the weight is supported by the femur, the thigh bone, and that is made from cortical bone. So we want to, basically what we have to find the maximum force which is applied on the cortical bone from this person, and then we'll compare with its weight. So we have the formula stress is equals to force divided by area. So stress multiplied by area will be equal to force. Area is given, area of cross section of the femur bone is given, which is 3.7 into 10 power minus 4. And stress is there on the cortical bone, the maximum tensile stress, that is 120 megapascal. 120 megapascal means 120 into 10 power 6. So when we multiply them, we will get the value for force. So when you substitute this, it is 120 or once. Sorry, that is tensile stress because it is under compression, so it should be 170, not 120. because the stress is compressive, not tensile, because it is under compression. So I should take 170, not 120. As a person is standing, like because of its weight, it tend to compress the bone. So it will be 170 megapascal. This will give us the value of the force, which will be 61,810 Newton. That's a force on the bone. Like the bone, this is a force on the bone. And what about, because we have to show it's about like 70 times, this force is about 70 times the weight. So weight is equals to mg, the mass of the person, multiplied by its gravity. So mass of the person is given here, that is 90, multiplied by gravity is 9.81. So 90 to 9.81, which is 882.9 Newton. Now to get the ratio, so force divided, because we want to show the person that, so that the maximum weight which can be supported is 70 times the weight of the person. Like weight of the person is 882 and the maximum force which can be there on the bone is about 61,000. So when we divide them, 61,810 divided by 882, that is about 70% or about 70.07 or 70 times you can also. Is it clear, this question?
Yes, sir.
So we
Yes.
calculated the maximum force and then we compare with the weight. And it is stated in the textbook that the femur can support 30 times the weight of a person. Explain how the structure in this diagram would account in a different from the calculated value. Like in a textbook, it is said that it can support 30 times the weight of a person. But why practically it will be different value? Because the area of the bone is not same. It is different at different places. So as the area is changing, the maximum force which can be applied on that, so can also change. Or area is not constant for this, and same thing, this is a femur bone, maybe it's having different types of bone, like cortical is there, and or part of it which is a cortical bone, that might be different. A proportion of the cortical bone might be different, that's why we will get a different result. So the area is different, you can mention, or the type, the bone may not be of same type, that may leads to a different value than the stated value in the book. So this is assignment related to materials.